Good evening, sir. Thanks for joining. I hope my voice is clear.
Good evening, sir. Yes, you are clear.
Thank you. Okay. So, good evening, everyone. Let me start the session. Um, we'll give a brief introduction so that we can wait for others to join also. Thanks for joining the fourth problem solving session of this course, NPTEL course, Wastewater Treatment and Recycling. I am Saravanan, PMR of Scholar and Prime Minister Research Fellow of NIT Tiruchirappalli, Department of Civil Engineering. And I am taking this course as a part of my PMR of deliverable. This is my fourth course, and you can see my older courses in integrated solid waste management, air pollution and control, plastic waste management, and this is my fourth course. So I am taking the problem solving session on every Monday 6 to 8 p.m. So we are in the fourth week. So first week we have discussed about what is the brief introduction about wastewater treatment and recycling, and in the second week we have discussed what are the sources of wastewater and how can we classify the wastewaters. And in the third week, we have discussed about the physical, chemical, and biological properties or parameters of the wastewater, like pH, turbidity, color, and chemical like alkalinity, hardness, BOD, COD, dissolved oxygen, and then biological parameters like coliforms, that is the fecal coliforms, and in the chemical we had nutrients, metals, heavy metals, everything we have discussed in the last week. So this week we are going to discuss about the treatment process. As we know all the parameters, if that parameters are exceeding, how can we treat the water? That's the aim, right? So for treatment process, we need to know about the reactors or reactor mechanisms. That's what we are going to discuss in this week. Yeah. Let me move on to the session. So first 1 hour we are going to discuss the same lecture material what professor has taught in the YouTube videos, and second 1 hour we are going to discuss the old assignment problems of the NPTEL course. Okay, so all the lecture materials are from Dr. Manoj Kumar Tiwari sir, Associate Professor of IIT Kanpur. So all the credits to him, and let me start the session. So coming to the wastewater characteristics quality. Oh, let me take that. So this week we are going to discuss about the fate transport of contaminant discharged in the river. So we know whenever there is a pollutant is discharged in the river, it will go along with the water, right? So it may transport and it may get disposed, or it may get degraded, or it may get increased. That's what that fate and transport of contaminants in the wastewater whenever it's discharged in the river bodies. So we have four discharge mechanism as I discussed in the first week. As per the Environmental Protection Act of India, we can discharge the treated effluent in four methods. We can discharge in the river, that is the surface water bodies. We can discharge in the marine. We can discharge in the inland uh, land surfaces. Fourth one is in the um, agricultural field. So these are the four methods to dispose the treated effluents. So whenever we are discharging in the river, what will happen? That's what we are going to discuss this week. Okay. So what happens when the wastewater is discharged in the river? See here in this figure, we know there is a river flowing. There is a wastewater that is coming out from a sewer line, and it's going to mix with the river water, right? So what will happen? Whatever the pollutant in this wastewater will get along with the fresh water in the river. So the what are the mechanism it may happen? First it may get transported, right? So there are four methods of transportation: advection, diffusion, dispersion, and leaching. What is advection? Whenever you are putting a paper in a water, I have given example here, right? If you see, whenever you are putting a paper in a water, it will float along with the water, right? Wherever it's moving, it will also go along with the water. That bulk movement is called advection. What is diffusion? If you drop a uh, uh, put a drop of ink in the water, river water, what will happen? the ink will not stay on its the same place. It will move from high concentration to low concentration. At the drop point, we have more concentration of the ink, but at the space moves, we can find the diffusion of the ink. That's what movement of high concentration to low concentration. Then what is called a dispersion due to variation in the velocity. If the velocity is more at the high point, because if you go below the depth, if you know in the fluids, you know the velocity variation inside the river, right? There is a, if you say, let me reduce it. So if this is the depth of the river, at the top the velocity will be higher. At the bottom, the velocity will be lower due to friction, right? Along with the bottom of the river. So velocity will be higher at the top, velocity will be minimum at the bottom, and we can find the average velocity at a point. So we can find the wherever the velocity is maximum, this variation will be higher. So like that, due to various parameters, flow parameters like discharge, velocity, or any other volumetric parameters, if it varies, due to that the concentration varies, then it is called a dispersion, right? So advection is the bulk movement, diffusion is the movement from high concentration to low concentration, dispersion is due to variation in the flow parameters like velocity. Then leaching is whenever there is a whenever you are putting any food particle in the water, it will get leach out into the water bodies, right? Or if you put any balls with the dye, then the dye from the ball will come out from the material to the water. That's called leaching. So this process is all called transport. Then phase transfer is relocation of the waste, like the sorption or desorption. Whenever you are having a small particle in the river, that pollutant will be absorbed into the small particles like sand or any charcoal, or it will get desorbed from the material to the water. That is called sorption and desorption. That's called adsorption or absorption. It may happen. Then volatilization, changing from solid phase to gas phase, is called volatilization, right? From the river, it may also go into the atmosphere. That is called volatilization. Like some of the oxygen, when it is there in the water, that may come out into the atmosphere. That's called volatilization. Any parameter may undergo volatilization. Then transformation and degradation, like any microorganism present in the water will degrade the pollutant that is coming into the water. That is called degradation, like biotic, abiotic, photodegradation. Due to sunlight, the degradation may happen. So this all are mechanism of uh, transportation or phase transfer whenever there is a pollutant coming into the river body. So transportation, phase transfer, transformation or degradation. Okay, these are all will happen. So when another one main aspect in the river is natural purification or self cleansing. So you are discharging one pollutant at a point in the river. The river is coming clean water with the clean water. Whenever you are putting a pollutant into the river, so the pollutant will after 1 kilometer or 2 kilometer, if you find the pollutant will be with less concentration. After 10 kilometer, there you can't find any traces of pollutant. Why it's happening? Because the river have a capacity to purify the river on its own. That's called natural purification or self-cleansing property of the river. So why it's happening? All surface water has the tendency to remove this type of conventional pollutants. Only for conventional pollutant, not for emerging pollutants. We had discussed emerging pollutant like pharma, pesticides and all. But normal pollutants like organics, nutrients, if it comes into the river, then due to the flow or due to the turbulence of the river, it may add up oxygen and it will degrade the pollutant on the river. That's called a self-cleansing or natural purification process of the river. Why it's happening? Due to physical, chemical and biological process that takes place in the river streams. So it varies with the flow rate, turbulence, nature of the river bed. Whenever the river bed is slow, then more turbulence will happen. So more turbulence will add oxygen to the water that will easily degrade. Then that type of biota present, variation in the sunlight. Whenever there is more sunlight, more photodegradation will happen. And temperature of the river, because the DO varies with the temperature, right? If it is cooler water, more DO will be present. So all this will help in the purification of the river on its own. That's called natural purification. No need of treatment is required. So how the natural purification is happening in the river due to the these are all the process. If you see dilution, because you are adding 1 milligram of pollutant in I mean 1 milligram of pollutant in 1 liter, that's a wastewater. You are adding in 1,000 liters of water that is flowing in the river. So it's a dilution process. So you can't find any traces of pollutant. That is called a dilution process. Then sedimentation. The pollution may get sediment deposit at the bottom of the river. That is called sedimentation. Then filtration. How the filtration will happen? There is a sand bed at the bottom of the river. So the pollutant may enter into the sand bed at one side and it may come out on the other side. That is called sedimentation, the filtration process of the sand. Then adsorption. Adsorption is the one whenever the pollutant is adsorbed onto the particles. That is called adsorption. The what pebbles or any sand that may trap the pollutant, and the river flowing outside will have a pure water. Then sediment transport, hydrolysis. Hydrolysis is again the process of addition of water that will degrade complex organic matter into simple organic matter. That's process called hydrolysis. Then biodegradation, due to oxygen transport, some microorganism may degrade the pollutant. Then photodecomposition, due to the presence of sunlight. So these are all process may enhance the self purification of the river. Okay, major processes: filtration, re-aeration. Due to the turbulence, whenever the oxygen got reduced, that will be taken from the atmosphere, right? Then sediment transport. See, the major processes: oxygen from the atmosphere is coming into the water, and you can find pebbles having biofilm at the surface of the pebbles. These biofilms are the consortium of bacteria, like a group of bacteria present at the top surface, that is the pebbles. Then it will take the oxygen in the water and it will degrade the pollutant. So oxygen will get reduced, but again due to the flow, the oxygen will be taken from the atmosphere. So this process is called self-purification, sorption and decomposition. So we are taking the oxygen, we are decomposing the organic matter, not we, the river on its own is doing, and then it's releasing carbon dioxide to the atmosphere. Yeah. So how can we classify this type of processes? Physical process like dilution, sedimentation, filtration, aeration, and the sediment transport. There is no need of any chemicals for this processes. So it's all happening on its like any force is helping this process, like dilution, sedimentation, filtration, aeration, and sediment transport. But physicochemical process kind of adsorption, because adsorption may be a charge principle, aggregation due to a bonding process like oxidation and reduction. These are all physiochemical processes. Then biological process like again oxidation, decomposition, photochemical process like photodegradation. So we can classify based on its nature of the process. How this natural purification will be impacted due to temperature and sunlight, because oxygen, what is the difference between mass transfer and mass transformation? No, yeah, it's a good question. Like if mass m1 is there, after 1 kilometer, if the same mass of m1 is there, like 1 kg, if you are putting here, after 1 kilometer, if you are finding 1 kg, the same 1 kg of mass, that is called mass transport. But if 1 kg of waste, it's getting degraded to 0.5 kg of waste, then there is a transformation. That's called a transformation. There is a reduction in the mass or increase in the mass. That's called transformation. Transfer is, it's a movement, transportation, right? Movement of one place to another is called transfer. Change on its property is called transformation. Hope you are clear with that, mass transfer and transportation. So can I move on?
Yeah, sure.
Yeah. So this temperature and sunlight will affect the oxygen in your water body. If temperature is more, less oxygen will be present. When temperature is sunlight is high, more photodegradation will happen. What is hydrography? The properties of the water like velocity, depth, turbulence, stratification, distribution of the sediments, DO, microorganism. These all parameters of the river water have impact on the self-purification process of the river. Then nature of the river bed. If it is having a more sand, then we will get more filtration, more sorption, desorption, nutrient uptake, and kinetics will also be based on this type of river bed. Okay, and the biota present. Then whenever there is a pollutant enter into the water, that we will get 4 zones, right? In river I am saying. So first the river is coming with the pure water, that is called a clear zone. All the microbes will be there, all the fishes will be active, alive, because the dissolved oxygen is more. Okay, so we are having dissolved oxygen up to this level, so that is called a clear zone. But we are having an industry here and it's disposing a wastewater here, or any sewage treatment plant are discharging the waste here. Then suddenly, due to increase in the BOD is what? More organic matter there is more BOD, right? So BOD is here first initially in the clear zone, that is getting increased due to the addition of wastewater, and in the course of time the BOD starts decreasing due to microbial degradation. And suddenly whenever the pollutant got coming in, the oxygen will get reduced, because the oxygen is taken by the microorganism to degrade the organic matter. That's why organic matter is degrading and oxygen is also depleting. Why it's again getting increased? Because we are getting oxygen from the atmosphere due to the turbulence process, right? So there is a deoxygenation happening, there is a reoxygenation happening. So the difference in both will give you the DO sag curve. That is the resultant DO. DO is getting decreased. The present DO is getting decreased, and the DO is added from the atmosphere. So the total DO will give you the uh, resultant DO. That is in this graph you can find. Initially it will get decreased, and after some point it will start increasing. So minimum point is called DO minimum point. That is a critical point. Okay. So now we can classify the zone. The addition point is called decomposition zone. At some point the degradation will be more, and after some point it is called a septic zone. The DO will be very less and there won't be any living organism. Again the DO will start increasing, that is called recovery zone. Finally it will get the first zone, that is called the clear zone. You got it? So whenever you are discharging any pollutant into the wastewater, it will first start decomposing and it will form very less or DO condition, that is called a septic condition. Then the third one is again recovery condition, again you will get a clear zone. Okay. This is the process. Then clear zone is the one which has its own saturated DO. What is saturated DO? At a given temperature, if it is the temperature is 20 degree, we can get a maximum DO of 9 milligram per liter, right? So whenever there is a maximum DO, that is called a clear zone. That's the original condition of the river. Then decomposition zone is just below the discharge of the wastewater. It will be very dark and turbid because we are having more organic pollutants, and the sludge will deposit here. See, more sludge is getting deposited, and then DO is reduced significantly because we have a addition of organic matter. So all the microbes will take the DO. So DO will get decreased and more deoxygenation will happen. Unfavor for the aquatic organism, only sewage fungi will be there. Fishes will start dying. Then septic zone, the DO will be very minimum. For the fish to live, what is the minimum DO required? 4, right? Whenever the DO is greater than 4 milligram per liter, then only the fish will live. Otherwise, the fish will die. So DO will be very minimum. So fish population is absent. Only the sludge worms and mosquito larvae are present in this kind of zones. Okay, then recovery zone. Again, the DO will start increasing. So water quality starts improving. BOD degrading while DO increases. Same BOD will always decrease. Initially decreases due to the consumption of oxygen. Again also it will consume and it will reduce, but the DO will be added from the atmosphere. So BOD will always be reducing, right? And the organic matter will start mineralizing. That means initially larger compounds will break down to simpler compounds and it will be converted to CO2 plus H2O. Any glucose or any organic matter will be converted into CO2 H2O. Organic matter will have C and H, right? So all this complex organic matter, whenever oxygen is added, microbes will degrade and it will be converted to CO2 plus H2O. The presence of algae again will start coming, and it's prominent to protozoa, rotifers. This type of macroscopic plants will start evolving. Again, clear zone will come. Got it? These are the 4 zones of river. It is very important topic in wastewater treatment. That is the self purification of the river. How we can find the self purification? We have some indices, right? Like physical indices like color, turbidity, and the suspended solids. We can classify the zones. Then chemical indices like DO, BOD, COD. If the DO is minimum, we can indicate that as a septic zone. Biological indices like MPN, that is the most probable number to find the fecal coliforms, colony forming units, and different microbes. Whenever there is a protozoa, we can find that as a recovery zone. Whenever there is only mosquito larvae and fungi, we can say that there's a septic zone. So we have indices to classify the zones. Okay, the stages of river can also be classified based on these 3 indices, right? So first we can take DO. Last week also we have discussed a lot about DO. DO is dissolved oxygen in your water. All the aquatic organisms require oxygen similar to human beings. It will also respirate through its fins, and whenever the oxygen is very low, the fish cannot live there, so it will die. So minimum oxygen required is 4 milligram per liter. based on the temperature, maximum saturated DO will increase. So if the temperature decreases, the DO will increase. uh, the saturation DO will increase, right? So at 5 degrees Celsius, more DO will be present. At 30 degrees Celsius, less DO will present. So if you add any wastewater, the DO will start decrease because the microbes will consume. It will again increase due to the addition of oxygen from the atmosphere. So we are getting a oxygen curve. So this dotted line, if you see, that is the deoxygenation. Oxygen is taken by the microorganism. That is called deoxygenation. Then oxygen is added from the atmosphere. That is called the reoxygenation. You find the D and re. There are two oxygen curve we can plot. One is deoxygenation, another one is reoxygenation. So if you add both, so here oxygen level is at this point of, if I am taking, or if you take 1 day, 2 day, or if you take 1 kilometer, 2 kilometer, time or distance both you can take. So if you take 1 kilometer, this point the DO is this is the deoxygenation, reduced the oxygen level and added oxygen level. If you add both, you will get this. At 2 kilometer or 2 days, this is the oxygen level. Here you can take it. This is oxygen, reduced oxygen level. This is increased oxygen level. So if you add both, you will get this. So at this point, you will get the minimum. Again, if you take here, you have this much oxygen reduced and this much oxygen added. So if you add, again it will get increased. This is called
Can
the
you,
oxygen curve.
can you
Sir,
repeat, please? Can you repeat, please?
this one, okay, let me draw, that will be better, I guess. So if you are your DO is initially at 9 milligram per liter, say, because the water temperature, if you are thinking as 20 degree, so 9 milligram per liter, that is the maximum saturated DO it is present. So I am adding a BOD, that is organic matter or any pollutant I am adding at this point. Okay, suddenly the DO will start decreasing, it will start reducing, and it will go like this because I'm having organic matter in my water. So all the microbes will degrade the organic matter with the presence of oxygen, because to degrade organic matter we need microorganism, we need oxygen. So it will get reduced. In the same time, due to the flow of the river, the oxygen from the atmosphere will be taken by the river. That is called re-aeration. This is deoxygenation. Again, re-oxygenation will happen. So oxygen will start increasing. So if you take total oxygen at this point, I am adding the water at 0 kilometer. After 1 kilometer or 1 day, water will travel to 1 kilometer in 1 day if you think. Then at 1 kilometer if I take, so the oxygen level is this much. 9 will reduce to 8. And I added, not me, the nature has added 1 milligram of oxygen again. So total will become again 9. Okay, at this point if you take, the DO was reduced to 2 and I have added another 2. So the total will be 4. And if you take this point, DO was reduced to 1. I have also added 1. So total will be 2. And this point, it was reduced to 0.5. And but I have added 5. So it will become 5.5. So if you draw this curve, the resultant curve, that is called the oxygen sac curve. You got it?
Yeah, it's okay.
Yeah. So this is the oxygen sac curve. So this is the resultant oxygen, the oxygen present at any time, DO at any time T. Okay. Yeah. That's the at which point the oxygen is minimum, that is called critical DO. D at DO at critical point is called DOC. At what time? That is called critical time, TC. Okay. Yeah. So at any point if you take, that is DO at any time T. So how can we find DO at any time T? Total oxygen, that is the saturated oxygen, minus the actual DO. That will give you the oxygen deficit. So why we need to find the oxygen deficit? Then only we can supply that much of oxygen to the water. If it is a river, it will take on its own. But if you think the same in your reactor in the wastewater treatment plant, that much oxygen deficit we have to supply. So 9 milligram per liter is my saturated DO, but I have only 5 milligram per liter at any time T. Then my oxygen deficit at that time will be 4 milligram per liter. That is the difference. So saturated DO minus actual DO will give you oxygen deficit, how much oxygen required. Okay, that is based on rate of deoxygenation and rate of reoxygenation. So water body to be clean, the oxygen deficit should be 0. That means the DO of the river should be maintained at saturation. Then it is a clear water. That's what clear zone. Okay. Then what is deoxygenation that I explained? Oxygen will go on reducing due to the breakdown of organic matter by the microorganism. So rate of change of BO, because why the oxygen is reduced? BOD is consumed. So how much BOD is reduced? BOD is LT, right? How much BOD is reduced is directly proportional to how much oxygen is reduced. So this KD, it's the rate of reduction of oxygen. That's called deoxygenation constant. So if you can integrate this and you can find this equation, LT equal to L naught into e power minus KDT. KD is deoxygenation constant. Okay, or a BOD reaction rate constant. Same if you think about reoxygenation. So reduction in the oxygen is due to consumption of BOD, but increase in the oxygen is due to atmospheric oxygen entering into the water bodies, right? So it's directly proportional to oxygen deficit, because while you are having more oxygen deficit, more oxygen will come from the atmosphere to the water. So it's based on the oxygen deficit. It's based on the depth of the receiving water. If you have a shallow river, then your increase in the oxygen will be more. If you have a deeper water body, then there won't be much oxygen entering into the water bodies. Then condition of the water body, running stream means more oxygen. If it's a stagnant, then not much oxygen will be entering into the water. And temperature, whatever which we know, the temperature is low, more oxygen will come in. So how the oxygen is coming in is called reoxygenation. It's not based on the BOD, it's based on the deficit. But deoxygenation is based on how much organic matter you are having in your water body, right? So deficit, as I mentioned, uh, at any time, a deficit equal to saturated DO minus DO at any time is called a deficit. It's not deficit, oxygen deficit. Okay. So how can we find the DO at any time? We have an equation called Stetafels equation. So we have a deoxygenation constant, we have a reaction constant, how much BOD we are giving in. Again, e power minus KDT minus e power minus KRT, reoxygenation constant, how much time? That time we need, okay, in 1 kilometer or 1 minute, how much, or 1 hour, how much? So that time we can add here. Again, D naught. D naught is your initial DO. Okay, initial DO, if it is not given, you can take as a saturated DO is our initial DO. E power minus KRT. Okay, so this is the formula given by Stetafels. So it's called Stetafels equation. Usually the deoxygenation constant ranges from 0.1 to 0.2. You can find the deoxygenation constant based on this equation, because deoxygenation will vary with the temperature. So always the deoxygenation constant will be given for 20 degree. So if you want for 10 degree, you can find 20 degree into there is a theta 1.047 power T minus 20. So T is 10. 10 minus 20, if you give whatever the temperature you want, you can give. Okay, always the KD will be given for 20 degree only. So based on this, we can find the KD. KR anyway will be given with the reoxygenation constant. Both if you substitute, you will get the DO at any time T. So if you know the DO at any time T, and if you know the saturated DO, you can find the deficit. So if you know the deficit, you know how much oxygen you need to supply, then water will become clean. You got it? Why we are having all this? We need to clean the water, or we need to treat the water. We need to find how much oxygen I have to supply. So for that, I need to calculate how much deficit is there. So deficit equal to saturated DO minus DO at any time T. So DO at any time T can be found with the KD, KR and time. With all this formula and BOD value, I can find. L naught is the ultimate BOD, ultimate first stage BOD. How to find L naught? LT equal to L naught into e power minus KT. So that formula also we have found understood at the last class. So if we have all these parameters, we can find the DO deficit with the Stetafels equation. Okay. See, as same like DO, BOD is also getting decreased, right? Because all the organic matter is getting consumed. So if less organic matter, less BOD. So BOD initially it will be the ultimate BOD that is getting reduced with the time, and it will become zero when all the organic matter got reduced. Then BOD exerted is how much BOD degraded. So here there is no degradation. After some time, this much is degraded. So we can draw here. So this is BOD remaining, this is BOD exerted, that is consumed by the microorganism. So how much BOD exerted is directly proportional to how much oxygen taken. Like that's the equation, LT equal to L naught into e power minus KT. That is LT is how much remaining. So how much exerted is LT minus L naught. That is the BOD exerted formula. L naught into 1 minus e power minus kt. That is L naught minus LT will give you this formula. So only two formula you can remember. LT equal to L naught into e power. L naught is the ultimate BOD. E power minus kt. K is deoxygenation constant. If you want, this is BOD remaining. If you want BOD exerted, that is how much oxygen consumed. If you want, then BOD exerted is L naught minus LT. So if we substitute this one, L naught will come out 1 minus e power minus kt. Right? So this is the formula. This please remember this two formula. BOD remaining is L naught into e power minus kt. Always they will ask for BOD exerted. That is BOD consumed equal to L naught into 1 minus e power minus kt. Yeah. So this two will be used to find the oxygen deficit. So if you see the relationship between the DO and BOD, DO changes is due the deoxygenation is proportional to the organic matter. But how much the DO coming in? Deoxygenation is based on the DO deficit. These are the two major principles you have to remember. So reduction in the oxygen is due to organic matter present. Addition of oxygen in the river is due to how much deficit, that is the oxygen requirement. Okay, this two you please remember. Yeah. So if you substitute all this formula and if you use the particular integral to solve this equation, you will get the final equation as State-Effels equation. dt equal to kdl naught by what we have seen in the State-Effels equation. Same equation you have studied. So if you remember 2-3 formulas, you will solve all the questions. If you could able to recall this formula, you can recall. Otherwise, this will not be asked mostly in the question papers. But these formulas are very important. LT equal to L naught into e power minus kt is the BOD remaining. BOD at any time t.
Can I interrupt, please?
Yeah, please.
Yeah. Somewhere I have found out that in place of E, it is using 10 to the power minus kt.
Yes. So when E should be used, when 10 should be used. That's the question, right?
Yeah.
Yeah. So if you want to be that is based on the integration. So if you are integrating based on ln, then you will get E. If you are integrating based on log 10, then you will get 10 power. That will be given in the question. The integration is based on base E or base 10. So based on that, you can find. We are going to solve one question based on this. So they will give you the integration we have done based on base E. Then you have to take the formula LT equal to L naught into e power minus kt. So if they have given based on base 10, then LT equal to L naught into 10 power minus kt.
Okay. Okay.
So that will be given in the question. Whenever how you derived this equation will give you the answer. So I have used E here. So if you use 10, you will get 10. So that's the integration part. Yeah. So from the State-Effels equation, what we can conclude 2 points. As I mentioned, wherever the DO is minimum, that is called critical DO. At what point is called a critical point, or what time is called a critical time, TC. So I need to find which point my DO will be very minimum. So that's called DC. How much it will be, that is called DC. So both I can find with this State-Effels equation. How I can find at that point, as I mentioned, it will be minimum. So whenever there is whenever a value is minimum, if you integrate that value, you will get 0. Sorry, if you differentiate that value, you will get 0, right? If I say A is minimum at a point, so if I differentiate A with respect to the time, I will get 0. So differentiation of any maximum and minimum value, you will get 0. That's what known principle. So if you differentiate that State-Effels equation and put 0, you will get to the time TC. If you substitute this time, you will get DC. So these two formulas you can get from the State-Effels equation. Okay. So Kr by Kd is the self-purification constant. How much reoxygenation is happening divided by how much deoxygenation is happening is equal to your self-purification constant. Got it? But this formulas you no need to remember, but please understand State-Effels equation is used to find DO at any time, and that can with that we can arrive critical point and critical DO. Fine. Okay. For any water body, you can check the F value as 0.5 to 1. And what is the limitations of the State-Effels equation? Here, the DO varies in the stream with respect to time, we can find. But here we have assumed only one single BOD input is given and it was distributed. If you have 2-3 BODs, 2-3 inlet points for a river, here I am discharging on organic matter, here I am discharging on organic matter, then this state of health equation will not work out. Again, we have to do a modeling studies. So this equation will be useful only if you assume single BOD input is distributed, right? And another concept, another limitation in this formula is only carbonaceous BOD is considered in this equation, and reoxygenation is due to taken by a DO source. These are the two problems here. And nitrogenous BOD is not considered. We have two types of BODs, right? In the first 7 days, BOD is carbonaceous BOD. After that, nitrogenous BOD. So total is called the ultimate BOD, right? That's what we have to study in the BOD parameter, right? That's why we are doing BOD at 5 days. So that is one of the limitation. And we have taken re-aeration only due to DO source. There may be some other sources of DO re-aeration also that we didn't take into consideration. And removal of BOD by sediments, conversion, only microbes we have taken. LT equal to L naught into e power minus kT is first order equation of microbial degradation. Other methods to remove the BOD like sedimentation, filtration may also happen. That is not taken into consideration. Okay, so it's a worst case formula only. We find what is the answer here, that will give you anyway worst case, that will be useful for your studies, right? Other processes are not taken into account. Yeah. Then if you see attenuation of pollutant on the land or surface water, as this much we have studied about whenever you are discharging a pollutant into the river body. But whenever you are discharging a pollutant into the land or subsurface, what will happen? Because subsurface means groundwater. That will not flow like river, but there is also some flow. But it will not flow like river water, and there is no possibility to take oxygen from the atmosphere. You got it? In the river water, we have an open atmosphere, that is a surface water. So oxygen may enter from the atmosphere to the river water. But if you think about subsurface, there is no possibility of addition of oxygen naturally. So what will happen if you are discharging pollutant in the land or subsurface? There is a more prominent absorption. Absorption becomes more prominent. Like as I mentioned, in the river water, re-aeration is more prominent, but in the subsurface water or land, absorption become more prominent because more solids will be there, right? In the land, more solids will be there. I am putting wastewater here. Whenever the wastewater is passing through the soil, it will get absorbed, and the pure water is coming out at the other end. So absorption becomes the more prominent transportation process. Like advection, diffusion, dispersion will not occur because there is no much movement. So bulk movement will not be possible. Transfer from high concentration, low concentration will not be possible. Leaching will not be. Leaching may happen because soil is there, so leaching may happen in the subsurface transportation. And runoff will be the most prominent. Whenever rainfall comes, rainfall will take this pollutant along with the groundwater. That is one of the mechanism in the groundwater. That is the subsurface water. Decomposition of organic matter is based on the microbes available in the soil or subsurface consortium. Then, whenever the wastewater is disposed in the groundwater, it's relatively lower mobility because it will not be fastly moving. It will be having less velocity, much lesser chance of natural transformation. As I mentioned, there is no natural addition of oxygen. So these are attenuation of pollutant on land and subsurface water bodies, right? So if you think about some small problems, please understand this problem. It will be very easy. So read the question, you will understand the question first, and then we will think of what formula to be used. Okay. The question is, the sewage of a town is to be discharged in the river stream. So after treatment or before treatment, they are discharging the sewage in the river. So river is having more water that is flowing with the flowing with the discharge value, like this much meter cube per day. That is always the discharge of the river. We are having, right, in the dam, this much of cubic feet is released from the dam, like that. There is a flow in the river water, like 1000 meter cube per day, 2000 meter cube per day, 1 lakh meter cube per day. That is the flow in the river. And rivers having a concentration of the same pollutant, like small concentration, 0.1. But I am adding a wastewater that is having small quantity, like 1 meter cube per day, 2 meter cube per day, and it is having concentration more higher, 1000 milligram per liter, 2000 milligram per liter. If I take one here, what is the pollutant given? Any pollutant like BOD or any pharma or any pesticide, if I take, so that will not be present in the river, 0.1 or 0.01. but in my wastewater it will be more, 1000, 2000. So if I mix both, after this point, I am mixing here, right? After this point, what will happen? It will get a mixed concentration. Q will be QR plus QS. 1000 will come, here 2 will come. So totally 1002 meter cube per day will flow here. That is for sure. That is the mass balance. But in the 1002 meter cube per day, what is the concentration of the pollutant? That can be found through this type of weighted average method. Okay. See the question. The quantity of sewage produced per day is 9. So sewage quantity is 9 million liters. But BOD is 350 milligram per liter. River 250 milliliters per day is the flow. Sorry, this is the liter per second. Think about the units. Here 9 million liters per day, 250 liters per second. If you convert 9 million liters, million is 10 power 6 liters per day. Day is 24 hours, 3600 seconds. So if you multiply, you will get 9 into 10 power 6 by 24 into 3600, that much liter per second. If you compare that with the 250, it is very less, right? 250 will be more. And then BOD of the river is 6 only, but BOD of the wastewater is 350. What is the BOD of the diluted water? After this point, there is a dilution. How much BOD will be there? Please multiply your quantity with the flow with the BOD, and flow of the river with the BOD of the river divided by the total flow will give you the mix BOD. Got it? So 9 into 350, 6 into 250 divided by 9 plus 250. Please convert the unit and then add. See here. 9 into 10 power 6 divided by 24 into 60 into 60 will be 104 liter per second. But my river is having 250 liters per second. Okay. So 104 into 250 milligram per liter, 350 milligram per liter. Added with 250 liters per second, 6 milligram per liter only. So total will 104 plus 250 will be the total flow. So if you take the weighted average, you will get the BOD of the mix. You got it? Yeah, this is the simple question to find the BOD of the mix or any pollutant. What is the concentration? Okay. So think about this question. A city discharges 1500 liters of sewage. Okay. 1500 liters of sewage in a stream, that is a river. River's flow is 6000 liters per second. Sewage is only 1500 liters per second, but the river is flowing with 6000 liters per second. That's why dilution will happen. The temperature of the sewage is 20 degree, but DO content of the sewage is 0. Because it's having more organic, there is no dissolved oxygen in the sewage. But the stream is having 90% saturated DO. If the water is 20 degrees Celsius, then DO will be 9 milligram per liter, or 0.9 terms of 9 will be 8.1 milligram per liter. Like that, this much of DO will be there in the river. Then find the initial deficit, DO deficit. What is DO's deficit? How much DO reduced is the DO deficit. How to find deficit? DO saturated minus DO at any time t. Okay. So DO saturated is 9.1 milligram per liter at 20 degrees Celsius. 90% of that will be 8.1. See, 90% of saturated DO. 9.9 of 9.1 will be 8.25 milligram per liter. That is the river water. River water is flowing with 6000 liter per second, having a DO of 8.25 milligram per liter. I am adding a sewage 1500 liter per second, having a pollutant or DO level. Any pollutant or DO if you take 0. So what is the DO at a mix point? Please multiply this to 6000 into 8.25, 1500 into 0 divided by total flow will be 7500, right? How much it will be? 6.6. So here 7500 liter will flow, but DO will be 6.6 only, because we have mixed 0 with 8.25. So 6.6 only will be there here. So at this point, the DO will be 6.6. So what is the deficit? I need 9.17, but I am having 6.6 only. So there is a lag of 2.57 milligram per liter. That is the deficit. So DO deficit equal to DO saturated minus DO at any time t. So at the mix point, that is the time t equal to 0, my DO is 6.6 and my saturated DO is 9.17, it should be. So the difference of 2.57 is lagging, that is a deficit. You got it. That is the formula for deficit. Do you have any doubt in this? If you want, I can repeat. So how to find the mixed concentration? How to find the lag? That's the concept here. You got it? Yeah. So if you have any question, please stop me in between. Then I will move on to the next question. Yeah. Thank you. So here, if you read the question, see the ultimate BOD of a wastewater sample is 87% of the COD. So ultimate BOD is L naught. We know that is the maximum BOD that is inserted into the wastewater. Inserted into the water body is equal to 87% of the COD. That is 0.87% of 0.87 times of COD. So what they are asking, COD of the wastewater is 300. So I can find the ultimate BOD is 300. Right? This is the ultimate BOD. Just the value is given in another form. Considering the first order BOD degradation, any microbial process will be with the first order only. Any adsorption process may take first order, pseudo first order, second order decay process, but microbial degradation will always follow first order kinetics. So BOD reaction will be first order. That's why the formula is LT equal to L naught into e power minus KT. They are asking consider the first order BOD degradation rate constant K as 0.23. That's a degradation constant. K as 0.23 per day. Always the constant unit is per day. Okay, without any numerator, per day is the unit. And then theta is 1.047. Why theta is given? Because K will be always with the 20 degrees Celsius. We need to find the K at another temperature. We need to use the theta. Okay. They are asking what is the BOD value after 3 days with the incubation period of 27 degrees Celsius of this wastewater. So at 27 degrees Celsius, what will be the degradation rate? So 20 degree 0.23. I need at 27 degrees Celsius. So I can use normal 20 degree into theta power t minus 20. Right? Theta is 1.047. T minus 20 is 27 minus 27. So I can get the K value. Simply the K value you can find. K20 equal to K20 into theta power t minus 20. Theta is 1.047 power 7 into 0.23. So K becomes 0.3. 0.23 becomes 0.3. Then now they are asking for BOD value. So how to find the BOD? BOD exerted will be, BOD exerted formula is L naught into 1 power 1 minus e power minus KT. Right? What is L naught? L naught is 0.87 into 300. 1 minus e power minus k is 0.31. T is 3 days. So if you substitute everything, just see here, 0.87 of 300 is 261. 1 minus e power minus k. What is the new k? 0.317 at 27 degrees Celsius into 3 days will be 160 milligram per liter is my BOD. At the third day, when I incubate for 27 degrees Celsius, this much BOD is exerted. You got it? Because I am putting it in the BOD incubator. So 160 milligram per liter was degraded. Any doubt in this? So degradation constant will always be with 20 degree. If they ask for any other temperature, please use the theta value KT equal to K20 into theta power T minus 20. Substitute the given 20 value. Then T's value if you substitute, theta is 1.047, you will get the 27 degrees Celsius value. Then use the LT equal to L naught into 1 minus e power minus KT formula. Okay. It's not LT, it's BODT. LT equal to simply L naught into e power minus KT. When we are using that, when we are using this, we please remember, this is when we need to find BOD remaining. This is to understand BOD exerted. What is the BOD value means? BOD exerted in 3 days. That is, this formula only you have to use. BODT equal to. You got it? Yeah. If you have any doubt, please stop me or you can ask any question at any time. Okay. This question if you see, for a wastewater sample, the 3-day BOD at incubation temperature I think today the content is more. It will drag another 5 to 10 minutes. Please be online. Maybe I will try to finish it up to 8 o'clock itself. Let me go faster. For a wastewater sample, 3-day BOD was given as 20 degree, was 200 milligram per liter. How to write this? BOD, comma, 3 days at 20 degrees Celsius. So this is the way of writing. Okay, equal to 200 milligram per liter is given. What they are asking, taking the first order BOD degradation rate constant. Constant is K, rate constant, 0.22 per day. At always given at 20 degrees Celsius only. Okay. Then what they are asking, 5-day BOD they are asking at 20 degree. So we need BOD 5 at 20 degrees Celsius is what? So first, how to find BOD 3, how to find BOD 5? So BOD 3 equal to L0 into 1 minus e power minus k. K is always same, 0.22. T is 3. Okay. How to find BOD 5? L0, ultimate BOD will not change. That is the maximum BOD. So L0 will be constant always. 1 minus e power minus k. K is also constant. T is 5 here. This is 5 days. So if you divide both, you will get the answer. See, you can, this value is given as 200. So if you substitute 200, you can find L0. That L0 if you put here, you will get the BOD 5 value. All the others are known values. K is known, T is known. Only L0 is required. So L0 you can find from BOD 3 is given. So L0 you can find. You understand? Substitute the formula 200 equal to L0 into e power minus k to 3t. So here you can find the L0 value. That L0 if you substitute in BOD 5 days, you will get the answer. You got it? Yes. Let me move on to the next question. I will give you a consolidated sheet of formulas. Only small page of formula I will give you that I will upload in the Google Drive. That will be easy for you to recall. Okay, that also I will upload. Only the formulas. That will be easy for you to remember. Yeah, thank you. Here, if you see this question, it is again very easy. See, 2 waste streams. I have a river. I mean, the 2 waste stream A is coming, and another one B. So there is a river here, or any wastewater is coming from A. Another wastewater is coming from B. Both are mixing and giving a river C. In Trichy, if you take Kaveri is coming, Kolidam is coming, and it is converted again to Kaveri. So that are all Ganga, one small river is coming, again it's mixing with Ganga, and then again Ganga is going. So A, B, C, 3 streams are going. Okay, that's the concept. Then the temperature of the river A is 20 degrees Celsius because it's coming from a hotter region. C is 10 degrees Celsius. Then why it's happening? Because there is a reducing temperature at B. We don't know X. Okay, it is given that 5-day BOD of a stream A, BOD 5, comma 20 degree is given. How much? 50 of A, river A. Okay, BOD rate constant at 20 degree is base 10. I think Sir has asked this question, right? Base 10 they given. So K is 0.115 at base 10. So you have to use the formula 10 power minus kt, not e power minus kt here. Okay. Please understand this. K is calculated with the 10 power. So we have to use the 10 power formula in the BOD formula also. Okay. And temperature coefficient theta is given. Okay. Then what they are asking, 5-day BOD of the C, river C. So BOD 5, comma, what is the temperature of river C? 10 degree. So this is what the question. I have to, what is the formula to use for BOD? BOD 5 equal to L0 into 1 minus 10 power minus K. K, what, because they are asking for 10 degrees Celsius. So K at 10 degree I need to know into what is the time T, 5 days into 5. Okay. So what is the unknown here? L0 is the unknown. K is the unknown. So what is the another one important value they have given, right? mixer to form a stream C, the temperature of the given. Okay, then I need to find the L naught. So L naught can be found through A stream, right? See, what is the A stream? 50 is given. 50 is the BOD of the A stream. So from that I can find L naught value 68.22. Another word is important. Identical ultimate BOD. So A is also having a ultimate BOD, B is also having an ultimate BOD of same value. So C will also have the same ultimate BOD. If I am mixing 10 milligram per liter, here also 10 milligram per liter, then again I am getting 10 milligram per liter. It's the ultimate BOD, not the mixed value I am saying. So ultimate BOD will never change. So 10, 10, again 10 I will get. Not the BOD, ultimate BOD. BOD is 10, again based on the Q value it will change. But if the ultimate BOD of the A and B is same, then I will get the same ultimate BOD in reverse C. So whatever the ultimate BOD of the A will be equal to the ultimate BOD of the reverse C. So I can find the L naught from this value. L naught is taken for 20 degrees, so I can substitute the same value of 20 degree here and I can find that. Then K for 20 degree, 10 degree I can find with theta power. What is the K value at 10 degree? K value at 20 degree into theta power T minus 20. What is T? 10. What is theta? 1.135. What is K? 20.115. Understand? You can find K10. That K10 you can substitute here into 5-day BOD of reverse C having the same L naught. So L naught from the A you can substitute here 68.12. All the known values are there. So 21.22 is my BOD 5 of the reverse C. Got it? You have any doubt in this? So in the formula BOD, in the BOD T formula, we need to know the L naught, 1 minus e power or 10 power, K we need to know, time T we need to know. So K is based on the temperature. If it is given at 20 degree and they are also asking for 20 degree, we can easily find. If they given the T at 20 degree and they are asking for 10 degree, we need to convert the K with the formula KT equal to K 20 degree into theta power T minus 20. So at what degree we need, we can substitute that degree here, and theta if you substitute, you will get this. That you can substitute here. At what time they are asking, you can substitute here. L naught if they given, you can substitute here. You will get the BOD. So all are known values. You got it? Yeah. Solve this question. These are all gate problems. Simple BOD DO problems. So if we practice, we will get to know where we need to use 10 power, where we need to use E power, where we need to use LT into 1 minus formula, where we need to convert K value. You all, if you practice, you will get. Got it? Yeah. So here if you see, the 2-day and 4-day BOD values are given. That means BOD at 2-day is 100. BOD 4 is given as 155. How it is increasing? Because at the 4th day more BOD will get exerted, right? More BOD got degraded. That's why 150 or 100 becomes 155. Now they are asking K value. BOD rate constant is K value. How to find? BOD 2 is L naught into e power 1 minus e power minus K. That is what we need. Both are at the same temperature because there is no temperature given. T is 2 days. BOD 4 value is L naught into L naught is same because same wastewater, same ultimate BOD. 1 minus e power minus K is common. T is 4th day. Okay. So if you divide both the values, that means 100 by 155 equal to L naught will get cancelled. 1 minus e power minus 2K divided by 1 minus e power minus 4K. So only K is unknown here. So cross multiply, take ln on both sides, you will get the value. You got it? So that's the formula. If two BOD values are given, very easy. L naught can be cancelled with the one formula. BOD T equal to L naught into e power 1 minus e power minus KT. With that one formula, you can solve all the problems. You got it? Can I move to the next one? That is the reactor part. As of now, we have understood the relationship between DO, BOD in the Street-Effels equation. What is the deoxygenation constant? What is the reoxygenation constant? What are their role in finding the deficit? Okay. At last, I will recall the formulas once again. Yeah. If you find any difficulty, please let me know. Yeah. So again, here there is a concept of mass balance. That's what the question asked in the first time it's in the lecture itself. What is mass transfer? What is mass transformation? Whenever there is a mass, it will always be balanced. That's what the first line of the lecture. See, um, let me go to directly there. Conversion of mass. Mass can neither be created nor destroyed. That is the mass balance concept. If you take 1 kg of sand, if you disperse everywhere, still if you find that 1 kg is there as it is, but the density is reduced, right? You are disposing that, but it will not get uh, reduced in weight. But same, if you have glucose C6H12O6, if you convert that to CO2 and H2O, still the mass is same. That's why we are using the equivalent weight or molecular weight. Whatever the carbon's weight, that is converted to the carbon dioxide's carbon weight. What is the oxygen weight? That is converted here. What is the hydrogen weight? That is converted here. So mass is neither created nor destroyed. It can change from one matter to another matter, or it will dispose in its area. You got it? That's the mass balance concept. Okay, that's what we are going to see in this lecture. So why we need a treatment system? Because whenever we are polluting a water with more than its natural purification process, we have discussed about natural purification process in first 1 hour. In that, the river has its own capacity to treat the water. But if the river Ganga is coming, or if one industry is discharging water here, so after 1 kilometer or 2 kilometer, it's getting purified on its own without any reaction, sorry, without any human requirement, it's regenerating on its own. But after 2 kilometer, another industry is discharging. After another 2 kilometer, it's clear. But at one point itself, 10 industry is discharging. How the river will regenerate on its own? After within 1 kilometer, another 10 industries. So we are polluting the river more than its self purification capacity. That's why we are not giving time enough to treat on its own. That's called pollution of the river. Okay, leading to the pollution of the rivers in India, like river Ganga, Yamuna, Kaveri. Also, we are assessing the condition of the Kaveri. We have a Kaveri Sea Center in the NIT Trichy. We are assessing the pollution level at different stretches in the Kaveri, right? So all the rivers in our nation gets polluted due to anthropogenic activity. Who is discharging the pollutant? Due to sewage treatment plant or due to any industry. That's why it's getting polluted. So there is a, if it is small pollution, then the river has its own capacity. If it is a large pollution, then we need to take care of the river. So yeah, there is an engineering system required to treat the water before discharging. That's why we need to do wastewater treatment. That's the concept of our whole this course. Okay, so we need to set a processing unit that will treat the wastewater before discharging to the river, so that the river can, so whenever instead of discharging 100 milligram per liter, I am treating 90 and only 10 is discharged. Like that, if 10 industries are putting totally 100, so river can accommodate. If one industry is 100, then 10 industries 1000, the river cannot accommodate. You understand? That way, there we need an engineering system for a conventional pollutant, not for emerging contaminants. Yes. So in the treatment, we need a standard physiochemical biological process, like what is the natural process the river is doing. We are mimicking the same, like filtration, the sedimentation, same process adapting from the nature we are using in the reactors. You got it? So the mass of the contaminant either physically removed or chemically or biologically transformed. Physical removal is settlement. 1 kg is settling on as 1 kg. Chemical and biological transformation is 1 kg is converted into different forms, or volatilization, it's converted to 0.1 kg, right? That is called a chemical transformation. So various treatment units in the form of tank, because all the sedimentation tank, aeration tank, settling tank, what we say, grid chamber, everything in the form of tank we are having in the treatment plant. Okay, that's called the reactors. So we need to know the concept of mass balance before designing the reactors. Got it? So what is mass balance? As I mentioned, any mass can either be produced or not destroyed. That's the conservation of mass. So accounting of all masses in a processor system confined under a control, because we can't analyze the mass without a control volume. So in the infinity, you can't say the mass is conserved. if you take 1 liter or 10 meter cube of tank, in that 10 meter cube, we can say this much mass is coming in, this much mass is going out. But if we take infinity depth of tank, infinity volume of tank, we can find out. So we need a confined volume. That's why we are taking 10 milligram of BOD per liter. That's this per liter is coming in place because of controlled volume. If you take only 10 milligram, then where that 10 milligram is present, we don't know. So we need a controlled volume. That's what the volume of the tank or a reactor, right? Again, if you coming to the concept of mass balance, what goes into the system will always come out of the system. Otherwise, it will be removed in the system. That's the process. Okay. So if you take a tank, I am putting 10 milligram of solid into the 1 liter of tank. So only 9 is coming out. So remaining 1 is settled in the tank. So mass going in equal to mass going out plus whatever the mass settled in the system. That's what mass accumulation equal to. That is the mass accumulation in the system is equal to mass coming in minus mass going out plus mass generated. There may be, if it is a solid, it will deposit. If it is a BOD, it may get transformed into other form, right? So CO2 will go out. So that we have to subtract. COD will be considered converted to another form. So that we have to add. So 10 is coming in, 9 is going out, 1 is settled or 1 is going out. So mass accumulation is equal to mass coming in minus mass going out plus mass generated minus mass consumption. Got it? That's what DO if you take as example. I am giving 10 milligram of DO inside and I am supplying with the aerators another 10. So whatever the coming out is having 10 only. So where the other 10 gone is used in the system. That's what consumption. Okay. Yes. So if you have a mass in the system, accumulation in the system, mass in minus mass out, mass generated, mass consumed. So mass balance. So if you take with respect to time, you will get a change in mass with respect to time equal to mass in, mass out, plus or minus mass reacted. Okay, it may be consumption or it may be addition. So plus or minus. So here given here, plus generation or minus consumption. So this is a basic formula. dm mass with respect to time is equal to mass in minus mass out plus or minus mass change with respect to reaction. So that's the total change in the mass. You got it? Yes. So why we need to take the controlled volume? Because only with the controlled volume, with the boundary, the concept is meaningful. Otherwise, it's meaningless, right? If it is an infinite boundary, we don't know where the mass is coming in, where the mass is going out. So we need, with the tank, we can find this a controlled volume. If you take the whole world, we don't know where the mass is coming in, where the mass is going out, right? So we need to set a boundary. That's called a controlled volume. So transformation reaction, mass of the contaminant present in the controlled volume at a given time. So that's called the volume of a specific reactor or a tank. That's what the flow of mass is completely mixed flow or a plug flow reactor. There is a two model of flow of mass. That's what we are going to see in the further lectures. See, based on the mass balance, specific condition can be given to the flow patterns. Like if it is a flow condition, based on flow condition, we can differentiate as batch process or continuous process. If you take 1 liter of tank and adding 1 liter of water, wastewater, I am wait for some time until it get cleaned and I am taking out the 1 liter, again adding another 1 liter. That is called a batch process. If you are having a tank, continuously the water is going in, continuously the water is coming out, treatment and coming out, treatment and coming out. So I am continuously adding, continuously it's coming out. Then it is called a continuous flow tank. If it's a batch reactor or a continuous reactor, we can split. Mixed condition. If you have a mixture in the tank, then it is paddles or a mixing system, then it's a completely mixed system. If you are having a pipe kind of structure, water is coming in, degrading. At the other end, it's degrading, fully degraded. So it's a plug flow condition, like a pipe flow. Type of contaminant, conservative or non-conservative, you can split. Whenever the pollutant is 10 milligram is entering, after 10 hours also, again same 10 milligram is there, then it is called a conservative pollutant. It's not degraded. But non-conservative is 10 milligram is degraded into 1 milligram. 9 is degraded or removed from the system. So that is called non-conservative. BOD or non-conservative. Conservative pollutants are like pesticides, pharma products are conservative pollutants. Right? Change with respect to time. Steady state or unsteady state. At the same point, 10 is converting to 9. But At the inlet point, always 10 is coming. At the outlet point, always 9 is going out. That is called steady state. I'm not talking about different spaces. I'm talking about the single space. What is the concentration at any time? So at morning 10 o'clock also 10 milligram is coming. Evening 6 o'clock also 10 milligram is coming. That is called steady state. Unsteady state is at some time 10 is coming in, at some time 9 is coming in, at some time 8 is coming in, and going out as 9, 7, 6 like that. Then it is an unsteady state. You got it? Yes. So we are going to discuss the same. So batch reactor means there is no mass coming in, there is no mass going out. Because we are filling the reactor, we are making it to treat, we are disposing. Then again another batch we are taking. It's like a first batch lab, second batch lab. First finish, go out, second will come in, finish, go out. It's a batch. So in the basic formula, dm by dt equal to mass in minus mass out plus or minus change in the mass due to reaction. So here there is no mass in, there is no mass out. Got it in the batch reactor. So only dm by dt is equal to plus or minus dm by dt reaction. We are going to solve this equation. Okay. Continuous reactor means all the things will be there. In will be there, out will be there, reaction will be there. So total will be taken into consideration. Then what is completely mixed tank? As I mentioned, see, there is a concentration 10 milligram is coming in. Once it is entering into the system, it will get completely mixed in the system. So I have a mixer here. So in the mixer, it will get fully mixed. So whatever the concentration at this point, this point, this point, this point, at the entry point, everything becomes same. Outside it is 10, but whatever inside it is mixed, it will become 5. And going out will always be 5. Because whatever here will go out. So mixing is happening at any point of time, it will get mixed and it will go out. So in a completely mixed tank, whenever it's coming in, it will get mixed and it will go out. That's called concentration inside the reactor will always be concentration outside the reactor. So this is one of the condition in completely mixed tank reactor. That is called CSTR. Here with the controlled volume, complete homogeneous mixing. Concentration of a substance in outflow remains equal to the reactor. That is another important point. Mass out equal to mass inside the system. Okay. Then plug flow reactor, if you see, as I mentioned, plug flow is a pipe kind of thing. At this point, the concentration is 10. At this point, the concentration may be 9. At this point, the concentration may be 8. So it's reducing in the course of time. It's not mixed. If it is mixed, all will become 7.5, right? So it's not mixed, it's flowing. Like you can think about chlorination. We are adding chlorine here. At a point of time, it will reduce the microorganism. That's the plug flow reactor. That flow in a pipe kind of thing is a plug flow. Fluid is mixed in the radial direction. So in this point, if you think the cross section, it's mixing in the radial direction, but it is not mixed longitudinally. Okay. Analogous to pipes, similar to pipe. So river will be in a plug flow condition, but the tanks in the STP, sewage treatment plant, will be completely mixed tank. In any chemical process, if it is a tank, then it is a completely mixed reactor with a paddle. Or we can use batch reactors without mixing. So each plug of fluid is considered as a separate unit. So this is a separate unit. This plug is a separate unit. This plug is a separate unit. Okay. Usually the velocity of the fluid in the plug flow is a constant. The flow is constant velocity. Okay. See, whatever the concentration coming in, 10 is coming in. After mixing, it will become 5. 5 is going out. But it is a completely mixed tank reactor. But plug flow reactor, see in 10 is coming in. After some time, longitudinally, it is degrading 8, 9, 8, 7, 6. Going out is 5. Okay. So radially it's mixing, but not longitudinally it's mixing. What is conservative, non-conservative pollutant? Conservative pollutant is if I am adding 10, it will come out as 10. There is no reaction happen. So in my basic formula, the reaction will become 0 because there is no degradation happens. That's called a conservative pollutant. But non-conservative pollutant, 10 is going in, it will happen some reaction, microbial degradation or anything will happen. 5 will be coming out, 4 will be coming out. So if we take a BOD or any organic pollutant, we'll follow the non-conservative pattern. Right? See, conservative means 10 will go in, 10 will be retained. Non-conservative is 10 will become 4. You got it? You got the concept. These are all about the reactors. Knowledge of conservative, non-conservative pollutant is very important because that will decide the reaction rate. that dm by dt reaction should be 0 or not is based on the conservative or non-conservative pollutant. So the question will be asked by mixing all these conditions. Completely mixed conservative and what will happen? Plug flow non-conservative what will happen? So this type of questions will be asked. Okay. So please understand the concept. Steady state, non-steady state. As I mentioned, at one point, the concentration with respect to time will not vary. So concentration with respect to time will not vary is 0. And concentration with respect to time is not equal to 0, then it's an unsteady state. I mean, mass is changing with time, mass is not changing with time. If mass is not changing with time, the change in the mass with respect to time will become 0. Mass is not changing with time means dV by dt will have a value. Okay, this is a unsteady, this is a steady state. So if they mention continuous stirred tank reactor and steady state, then left side will become 0. If they mention steady state conservative pollutant, then left side and right side will become 0. Mass in will be equal to mass out. Okay, you got the conversion of formulas, right? Yeah. So at one point, at any time, the mass should not change. That is called steady state. Yes. So all this is giving the reaction kinetics. Transformation reaction occurs for a degradative compounds like organics. Mass is reduced with respect to progressive time. At any time, the mass will reduce, right? So dC by dt will happen. So it will be surely unsteady state. When this net rate of contaminant, this is based on dm by dt reaction. It's not about the left side dm by dt. This is based on steady or unsteady. But this reaction is based on conservative or non-conservative. So organic matter will give you dC by dt, but that not affect your left side. When this net rate of constant mass reduction become equal to the mass conservation inflow, then the mass of contaminants become stable, constant. The reaction is said to have a steady state. Okay, so nth reaction order will be dC by dt will be Kc power n. That is the kinetic constant at the nth order. First order, if you take n will become 1. So dC by dt will be Kc. All the organic degradation, microbial degradation will be first order. Most popular model for the rate estimation. That's what monod kinetics we are going to see in the upcoming weeks. So this and all, please remember the left side dm by dt is not equal to the right side dm by dt. This change in the mass with respect to time is equal to mass in minus mass flow, mass out. That and reaction that is happening plus or minus inside the reactor. That is based on the conservative or non-conservative. This is giving you the steady or non-steady. Yeah. So continuous flow reactor will always be steady state, right? Until and after it reaching a point, it will become a steady state. See, in a continuous tank reactor, initially it's having a pure water. I am adding the wastewater, so it will mix fully. So at that time, the concentration will reduce. So after it reaching a constant saturation point, whatever coming in will mix with this and go out. This will be always 5. So until it is getting 5, from the pure water to 5, it is the saturation point. After saturation point, it will be a steady state. Until a saturation point, it will be a unsteady state. So this is what modeling of the tank reactors. Okay, you got it. So continuous tank will be a pond or a lake having inflow and outflow. Plug flow will be for a river. Okay, we are mimicking the natural process in the reactors. On the other hand, if you take batch reactors only one, there is no inflow outflow. So always will be unsteady conditions, right? If it reaches a steady condition, we will discard because we need 5. Whenever it reaches 5, we will discard. After another batch 10 will be inserted, it will be 10, 7, 8, so 8, 7, it will reduce. Again, it will reach 5, we will discard. So batch will be always unsteady. If it reaches steady state, we will discard. There is no meaning of operating it further. Okay. Yes. So think about the basic formula dm by dt equal to mass in minus mass out plus or minus dm by dt reaction. Consider this with the volume because we are using all with the controlled volume. So V dC by dt equal to, if you multiply V with the mass is milligram, then if you take milligram per liter into meter cube per second, so this will be cancelled and milligram per second, that's the mass per time dm by dt, right? Milligram per liter is Q, mass is m, liter is v. So milligram per liter is mass, sorry, milligram per liter itself a mass. So qm will be giving you milligram per second. Okay, that's what the mass conversion per tank. So v dc by dt equal to q in c in minus q out c out plus or minus v dc by dt of reaction. Yeah. Please come to the application part. I'm thinking about the continuously mixed tank. What is continuously mixed tank? What is the concentration in the tank? It will be coming out, right? So what is the coming out? In the basic formula, I will change the out as C and the reaction also C. Okay, this is the continuously mixed tank reactor. V into dc by dt the same formula I am taking, and I am taking the C out as the same C and this C as C. See, V dc by dt equal to Q into C in minus Q into C plus or minus V into K. Why this becomes the first order? Because always continuous, it's microbial degradation, so K into C power n. Right? So V into K into C power n. That is the reaction. dm by dc by dt I am converting to K into C power n. First order means K into C. Okay. Same continuous mixed system, I am taking steady state. What is steady state? The left side will become 0. So if the left side becomes 0, this becomes 0, what will happen? This all can go this side, and if you convert this formula, C equal to C in into 1 by 1 plus kV by Q. So you can remember this formula, it's very easy. C equal to C in into 1 by 1 plus kV by Q. How it's coming? If you take steady state, this will become 0. If you take this to the left hand, you will get. If it is unsteady, this will not become 0. But the initial, if it is a conservative pollutant, this will become 0. As I
Can you
mentioned,
repeat, please? Can you repeat, please?
yeah, I will repeat. So the basic formula is V dc by dt equal to QC in minus QC out plus or minus V into dc by dt reaction, right? The reaction I am converting to first order reaction. And if it is a mixed system, continuously mixed system, I know the C out will be equal to this C. So C and C will be same. And if it is a steady state, the left side will become 0 because there is no change of concentration with the time. And if you take this to the left hand side, and the first order means N will become 1. So C will be calculated with at any time can be calculated with C in 1 by 1 plus kV by Q. This is the formula. If it is a unsteady, this will not become 0. Okay, left side will not become 0. But if it is a conservative pollutant, there is no reaction happening. So conservative K into K will be 0. So Q in C, QC in minus QC, this side will be having a value. So equation will become like this. If it is unsteady, first order, and no inflow concentration means C in will be 0, no inflow. Again, it will become a batch reactor kind of thing. So it will become this equation. Please remember only this equation. It is very important. Steady state condition, because always the continuous reactor will attain a steady state and it will be operated always at the steady state condition, continuous tanker. So this formula will always be valid. You got it?
Okay, thank you.
Yeah. Basic mass formula is change of mass with respect to time is mass in, mass out, plus or minus change in the mass with respect to the reaction. So I have converted it with the V value. So Q, V. So this I have converted into Kc power n. So this is another basic formula. So you can apply any zeros based on the conditions. If it's a plug flow, what is the condition? The same V is dc by dt QCx. I have taken this as a single point. After some distance, small distance dx, it will become x plus dx. So I am substituting in my in, out, small area I have taken. In this area, in is this, out is this, with a space of dx. So if we substitute and get this reaction value, dc by dx equal to plus or minus a by q dc by dt reaction. In this formula, basic formula, if I take a steady state, left side becomes zeros. A steady state means left side will become 0. So you will get this formula C equal to C in into e power minus kV by Q. C in into e power minus KT. V by Q will be T. Okay. If it is a batch reactor, what will happen? There is no inflow, there is no outflow. C in will become 0, C out will become 0. This 2 will be there. So basic, this formula will come. dC by dx equal to minus k power Cn. That is what our LT equal to L naught into 1 minus e power minus kT formula. Okay. So please understand, batch reactor means in and out will be 0. Steady means left side will be 0. Conservative means reaction will be 0.
Can I interfere, please? Can
Sorry,
I
sorry.
can, can, can I interfere, please? One.
Yeah, please.
Yeah. In case of steady flow
Yeah.
and non-conservative state, so the concentration in the reactor and
Uh,
concentration in the outflow will be
uh.
similar, or it will be different.
In the continuous tank, you are asking.
Hello.
In the continuous tank, you are asking, or in the batch reactor?
In a continuous
Okay.
state,
You are talking
CST.
about the continuous tank. There is an unsteady, right? And it is a non-conservative. If it is unsteady, then it will not have a. It's not considered as a continuous tank until it's becoming a saturated condition, steady state. It's not considered as a continuous tank. After reaching the steady state only, it's a continuous tank. That time C will be equal to C out.
Okay.
Okay, so this will take minimum time, like initial 1 hour or 2 hour. After that, for how many month we will operate at steady condition. Initial start of the point, any tank, we will initially operate at unsteady because completely it should mix. Then it will be a steady state. But batch reactor always follow this only. Unsteady. Hope it's clear. During this time, C out will not be equal to the C. C is the concentration inside the reactor. Yeah. Thank you. So, where we can apply this for the design of any treatment plant. If you are from a chemical background or if you are from a wastewater and water treatment background, any reactor is based on this 5 principles. So, please use this basic formula. You can design any of the reactors. Okay. You have to assume whether we are considering as a batch reactor. SBR, like sequential batch reactor, will take as a batch condition. If it is a ASP, like advanced oxidation, ASP is like aerated sludge process, then it is a continuous tank. If it is a plain sedimentation tank, then that is also a continuous tank. In and out will be there. So wherever mixing is there or not mixing is there, that also you have to take into consideration with reactions. Okay, based on this we are going to treat, and based on the degree of treatment required and the final concentration or how much out should come, that much treatment I will do. Okay, if 10 is going in, my effluent standard says BOD should be 30 when you are discharging in the river. So I am having 100 BOD in my wastewater. So I have to treat 70 so that I will get 30 that can be discharged in the river. Okay, 70 should be treated. How much aeration I have to give? How much DO I have to give? So that is based on the deficit I can calculate and how much that much air I will supply and I will treat in the tank. Okay, so this is a basic principle. Also, I can identify how much sludge is accumulated in the tank based on the accumulation formula. How much mass accumulated that I can take and treat. I can identify with the design itself before treating. So that's the design part. Some problems I can do. See, a pollutant is following first order decay and it's in a lake water. So it's a lake. Lake you can take as a tank and it's a first order decay. Half-life is 120 days. What is the half-life of a pollutant? If it is 100, initially the concentration of the pollutant is 100 milligram per liter. How much time it take to degrade to 50 milligram per liter? That is half of the initial concentration. Then it is called a half-life. Okay. The calculate the rate constant and time required to achieve 10% of its initial concentration. They given how much time it will take to reduce to 50%. That is the half-life. Now they are asking how much time it will take to reduce to 10% of the initial concentration. So T half is 120 days. They are asking what is T10? How much? So if it is a lake water. So there will not be any inlet, there will not be any outlet. Lake is a stagnant water, right? So it's a batch kind of thing you can treat. C in will not be there, C out will not be there, both will 0. So V dc by dt equal to minus this reaction alone will be there, k c power n. It's the first order. So C will be n will become 1 and V will get cancelled. So dc by dt equal to minus k into C. So dc by dt if you integrate, you will get this formula C equal to C naught into e power minus kt. The same L into L naught into the formula. No? Same formula you can use. So C naught initial concentration we don't know. That we can find with the half-life. C half equal to initial we don't know, e power minus k we don't know, time is 120 days it's taking. Now they are asking what is the C of 0.1, initial we don't know, e power minus k t we have, they are asking. So how to use this formula? C, we know C half is initial by 2, right? If it is 100 it will be 50, if it is 200 it will be 100. So this is known value. So here unknown is only k. If you find the k, substitute here, right? You will get the t value. So t is 400 days. Within 400 days your pollution will become pollutant will become 0.1 times of initially 100 is there. To become 50 it takes 120 days. To become 10, that is the 0.1 times. To become 10 it will take 399, that is 400 days it will take. So that's the time requirement. If I am discharging in the river, after how many days? So 400 days, how much distance it will travel? So if I am discharging in Tiruchi, at Tanjavur, how much BOD will be there? So I can calculate, right? So at the course of river, I can find what is the pollutant at any time without taking the samples, right? So if you think about this problem, see, the CSTR reactor, completely stirred tank reactor or completely mixed reactor. CSTR is completely stirred tank reactor. Volume is 400 meter cube. Volume is given. There is a single inlet. So Q is 40 meter cube per hour. Okay. Concentration of the pollutant is 20 milligram per liter coming in. Okay. That pollutant may be anything. They are saying this hydrocarbon as a pollutant. I can take anything like a pollutant as a pesticide, something. So determine the steady state. Steady state is given. So V into dm by dt becomes, so dc by dt becomes 0. C in, QC in minus QC out. This is a basic formula. Plus V into dc by dt or k into c power 1. It's a steady state first order decay. So c power 1. K is given as 0.27. Okay. What is the volume of the corresponding plug flow reactor? If I do the same in the plug flow reactor, what is the volume required? So I can compare the volume of a plug flow reactor and a completely stirred reactor, and I can choose if the land area is small, which treatment process I can use, I can decide, right? So based on this, you can find. See, now if the degree of pollutant reduction is needed, same degree of pollution reduction is needed. So how much initially treated, I have to know. Then the same I will apply for the plug flow. See, first steady state, so this becomes 0, and in the completely mixed, C naught will be equal to C. So the same formula if you use, C equal to C in into 1 by 1 plus kV by Q. That's the steady state CSTR condition. C out will be equal to C. So this is the converted formula. C equal to C in into 1 by 1 plus kV by Q. Hello, am I audible now? Hello, am I audible now?
Yes, sir.
Yeah. Sorry for the power cut here. Let me continue. So here condition is completely stirred tank reactor, steady state. So C out will be considered as C. So the final equation is C equal to C in into 1 by 1 plus kV by Q. So what are the given values? K is given, volume is given, Q is given. So I can find the C value. C is 5.4. If I treat with the completely stripped tank with this time, with this volume, I can get the concentration of 5.4 milligram per liter. If I question they have asked is what is the volume of the plug flow reactor if I go with the same degree of treatment? So C in should be 20, C out should be 5.4, same Q, but V is not V is unknown. How to find with the plug flow reactor? Plug flow reactor steady condition equation is C out equal to C in into e power minus kV by Q. That's the final formula we have got. C out we know, C in we know, K is known, Q is known, V we can find as 194 meter cube. You got it? So from this, I will show you this formula. C equal to C in into e power minus kt. அல்லது yeah, kt, t is v by q. Time equal to v by q. Meter cube by meter cube per second. So second will be there. You got it? And this continuously mixed reactor, this is the final formula. C equal to C in into 1 plus kv by q. You got it? Hello? Is my network is fine now? Yes, yes. Thank you.
Yes, sir.
Yes, yes. Because I'm using my mobile network for some time. Yeah. Okay. So you have understand how much the volume changes for completely mixed and plug flow reactor, right? Now, this is the startup of CSTR. The question what Sarah has asked us. See, startup of CSTR is, as I mentioned, initially, if you are having a completely mixed system with the 10 is coming in, uh, 5 is going out, then 5 will not be inside. Actually, completely mixed reactor, C out should equal to C, right? But initial time, sometime it will not be similar. That's what the startup of CSTR. It will not follow steady state. It will be unsteady, right? That's the question. 500 meter cube CSTR volume is given, filled with the clean water. So filled with the clean water is starting process. Initially, it will not be filled with this water, right? Clean water will be filled with the full of microbes and then containing 100 milligram of conservative pollutant. So they have a 100 milligram of conservative pollutant already, and flow rate is 50. The water that is coming in is 50 meter cube per day. The outflow channel also started simultaneously. Initially, they will start the outflow, but concentration will not be equal. So they will take out and again insert for some time. Outflow channel was also started simultaneously to ensure the extra passage of extra water in the pond. Calculate the pollutant concentration in the outflow at the function of time. So they are asking in this unsteady state condition, what is the equation? So pollutant concentration at a function of time. Is my voice clear now? Sorry for the network issue. Yeah, thank you. I'll continue. So the question they asked is, initially the tank is filled with clean water. So that is the startup of completely mixed. So it will not follow steady state. It will be a unsteady condition. So C out will not be equal to C because continuously steady C out will be equal to C. But here C out will not be equal to C. So this basic formula I am taking. Steady state, sorry, conservative pollutant. So this becomes 0 because conservative pollutant will not undergo any degradation. So this becomes 0. I have this equation. I have to rearrange and get this formula as a function of time. So out C will be equal to, C out will be equal to 100 1 minus e power minus 0.1 t. That's the answer. Okay, you got it? So the answer is in the as a function of t. Okay. I'm so sorry for the network issue. Am I audible now? Shall I continue? Hello. I'm so sorry, my network got disconnected. Am I audible now?
Yes, sir. Now it's audible.
Yeah. I'm so sorry for that.
Yes,
I will share my screen now. So is it visible now? Screen, yeah.
Your screen is not visible.
Now, can you please check?
Yeah, now it's visible.
Yeah. So that's all about the lecture material. So the whole formula what we have discussed today is, let me discuss. In the BOD we have discussed LT equal to L naught into e power minus KT. So this is time, small t. So if you want BOD at any time t, that is the BOD exerted at any time t is equal to L naught into 1 minus e power minus KT, right? K will be found at 20 degrees Celsius, that will be given. If you want any time, any temperature, KT equal to K20 into theta power T minus 20 is the formula. Theta will be given at any temperature. If you want, you can substitute that temperature. That's the formula we have seen. Okay. And DO deficit is equal to DO saturation minus DO at any time T. How to find DO at any time T? If you asked at the mixing point, then Q into DO of the river, flow of the river, sewage flow, DO of the sewage divided by total flow, QR plus QS. You got it? Then you can find the mixed DO that you can substitute here. That's what you can find based on the dispatch minus C. Same formula we have found in the reactors. Mass at any time T is equal to change in the mass at any time T equal to mass in minus mass out plus or minus change in the mass with respect to time on reactions. Okay. If you substitute with the V, because we need at a controlled volume, V dm by dt equal to Q m in, or C you can take, minus Q m out plus or minus V into, if it's a first order reaction, K C power n. Right? You got it? So based on the conditions, if it is a steady state, left side will become 0. If it's a conservative, right side will become 0. If it's a batch reactor, in and out will become 0. If it is a continuously mixed reactor, at a steady state, again left side will become 0. Mass out will become equal to the concentration inside the tank. This two will become same. You got it? This is the overview of what we have discussed today. Right? So if you have any question, please post it in the chat box. I will answer, or I'll go to some of the problems related to today's lecture. Hope you are clear. I will upload some formulas in a single sheet and I will give you as a material. Okay, can I move? Please post your answers in the chat box. I'll just rush through the assignment problems. Okay. So please answer this question. Identify the correct statement. Natural purification process only happen in daytime when organic matter is present in the wastewater and photodegraded. Natural purification process in the river are able to remove only decomposable organic matters. Which is correct and which is wrong? Natural purification may, let me take the pen, not only in the daytime. If oxygen is there, evening also it may happen. So this statement is wrong. Natural purification processes in the river are able to remove only decomposable organic matter. Others will not be removed, right? So statement 2 is correct, statement 1 is wrong. Decomposable organic. Yeah. Other matters will be transported, diffused, sedimented. So that is also wrong. Only decomposable. Natural purification process can remove any pollutant by different methods, like sedimentation, filtration. That may also happen. Only decomposable organic matter will be degraded by microorganisms. Others will be deposited. Yeah, D is correct. Correct. Let me move on to the second question. See, surface water, it may remove at any time always it will be present, natural purification, and it will remove any type of pollutant other than any type of conventional pollutant other than conservative pollutants. Yeah. Can you match the process and the type of processes?
Sir, you are not audible.
Yeah. I got disconnected. Now it's fine.
Yeah, now it's audible. Yeah.
So can you correct the process with the type of processes, like adsorption and activated carbon is sedimentation, BOD decay. BOD decay is biochemical. Sedimentation is physical, normal sedimentation. Adsorption on the activated carbon is physiochemical. There may be some charge property. So 1C is correct. You got it? Yes. See, physical processes, dilution, separation, sedimentation. Physicochemical is adsorption. Biological is decomposition or decay. Photochemical is photodegradation. Yeah. DO deficit in a river water means, what is the deficit formula? DO sat minus DO at any time, or DO at any time, or actual DO. So difference in the saturated DO and the actual DO. If it is a minimum DO, then it is a critical DO. Okay. So this is wrong. B is correct. Yes, B is correct. Oxygen deficit is saturation DO minus actual DO or DO at that time. In the septic zone of a river, receiving wastewater discharge, what will happen? BOD is 0, BOD is maximum, BOD is minimum, BOD is neither minimum nor maximum. Septic zone. So DO will be minimum at the septic zone. Clear zone, decomposition zone, septic zone, recovery zone, again clear zone. Right? DO will be minimum, but BOD can be anything. Reducing, BOD will get reduced. BOD can be 0, maximum, minimum, anything will happen. So we don't know. At septic zone, DO is minimum, but they didn't mention anything about BOD. See, BOD will keep on decreasing. Minimum will happen at the end, again at the clear zone only. Yeah. In a river, receiving wastewater discharge, the Streeterfeld's equation may use determine why we are using the Streeterfeld's equation to find DO at any time t based on KD, KR values. At the t value, we are finding the deficit. So Streeterfeld's equation is used to find how DO varies with downstream distance, at which river stretch DO will be minimum, because it will give you the critical point also and critical time also. So at which river stretch we can find what is the minimum DO value, that also we can integrate the formula and we can get the formula, right? So all the above is correct. Streeterfeld's equation is giving all these values. See, Streeterfeld's equation will give you dt. Also, it give you critical time, critical distance, at what time the DO will be minimum. Everything we can get with the Streeterfeld's equation. Get it? Yeah. Answer the question. DO changes due to deoxygenation is proportional to. There are two conditions happening: deoxygenation, reoxygenation. So D is due to degradation of organic matter. Re is due to oxygen deficit or oxygen taken from the atmosphere. So deoxygenation is happening due to organic matter percent. Reoxygenation is due to DO deficit. More deficit is there, more oxygen will be taken from the atmosphere, because the water need oxygen. Yeah. See, DO changes due to deoxygenation is proportional to the organic matter. Reoxygenation is proportional to the deficit. Got it? Yeah. So this is the again a basic mass balance equation: V dc by dt, Q in, Q C out minus V dc by dt reaction. The last term in the right hand side, this term VCD by dt reaction, are considered as 0. When it will be considered 0? When the pollutant will not go any reaction. It's a conservative pollutant, right? If the pollutant is a conservative, no reaction will happen. Correct. Sorry if I am going fast. Please read the question. You will understand. I will upload the material and the video in the YouTube. You can also pause the video and you can understand. Conservative pollutant, light side will become 0. Yes. If a conservative contaminant is released at the inlet concentration C in discharge Q, V steady state concentration. What is the contaminant in the outlet? A conservative contaminant is released. C in. What is the outlet? Any tank, batch tank or a plug flow or a continuously mixed tank. C in is going out. It is a conservative pollutant. Whatever mixing happens, whatever the volume, conservative pollutant will come out as it is. Right? There is no reaction happens. It's not 0. So C in is correct. Because it's a conservative, it's a steady state, there is no reaction happening, so everything will come out as it is. Yeah. Got it? Yes. Rate of change of concentration of a pollutant is found to be directly proportional to the concentration of the pollutant. So dC by dt is directly proportional to rate of change of pollutant. Rate is time. Rate of change of pollutant is directly proportional to concentration of the pollutant. The type of reaction kinetics is, if it is directly proportional to C power 1, that is the first order. If it is directly proportional to C square, then it is the second order. Right? If it is directly proportional to a value or a constant, then it is a 0 order reaction. How to draw this? Anyone know how to draw this? Erase all in one slide. Let me draw this. If it is see, there is no reaction, then it is a 0 order or a single value. First order means, sorry, this is a first order, 0 order. It is that dC by dt is a constant. We will go with the constant value. If it is a this is first order reaction. This is a second order kinetic. This is a 0 order kinetic. Got it? Based on the dC by dt equal to constant or C or anything. Okay. C. First order kinetics dC by dt equal to K into C or directly proportional to C. The proportionality is converted into constant. In a plug flow reactor operating under steady state, plug flow steady state, at any point the concentration is same at any time. Okay. Pollutant concentration may differ at different part sections. Yeah, at a different section it will be different. It's a plug flow. Okay. Inside the reactor. However, concentration does not vary with the time at any particular section. Any particular section, concentration will not vary with the time. So this is correct. Concentration inside the reactor is same everywhere. So this is wrong. This is a continuous tank reactor. Concentration may be different at a different point. That is correct. Inside the reactor. Concentration may also change with the time. No, it is a steady state. It will not change. Concentration inside the reactor is same everywhere. That is also wrong. So first is correct. You got it? If it is a plug flow and a steady state, this is correct. Yeah. So again they have given a batch reactor. So C in and C out is 0. So understand the reactor itself, you can understand the formula. 2 kiloliter wastewater. So volume is 2 kiloliter. There is no flow will be given. Only batch reactor means volume will be given. 20 milligram of lead pollutant or methylene blue is a pollutant. So 20 milligram per liter of pollutant is there. Underway first order decay. So Ct equal to C naught into e power minus Kt is the batch reactor formula. Rate constant is 0.25 per hour. So 0.25 per hour is the rate constant. So T is, they are asking what should be the reaction of retention of the batch if treated water should be 1. So outlet concentration is 1, inlet concentration is 20. What is the time taken to become 20 become 1? So e power minus K is given, T is a required value. Okay, you can find. K is 0.25 per day, per hour. So what will be the T's unit? Hour. If it is per second, T will be second. Okay. So if you substitute, you will get the answer. C equal to C naught into e power minus Kt. C is 1, C naught is 20, T is unknown, K is 0.25. Yes. Another CSTR tank. Volume is given as 500. Single inlet. So C in is given. not Q in is given. With the unit itself you can find 50 meter cube per hour. C in is 600 milligram per hour, milligram per liter. What would be the approximate steady state COD in the outlet? COD is the pollutant. They are asking what is the C out. C out is equal to C. It's a continuous tank. So what is the concentration here is equal to C out. Assuming the COD decay is 0.36. So what is the formula for CSTR? C equal to C in into 1 by 1 plus KB by Q. This is the formula, right? So K is given, volume is given, Q is given, C in is given. So we can find the C out or C inside the tank. Both are same, right? Use this formula. C in 1 by 1 plus KB by Q. K is given, V is given, Q is given, C in is given. You got the formula? Yes. Right. Here if you see 15 mld wastewater is wastewater stream having ultimate BOD. So we have a 15 ml wastewater stream. It's a river is there. On wastewater stream is coming. The Q of sewage or wastewater is 15 mld. Okay. BOD of the wastewater is 250 mld or L or any pollutant if you take C. 240 milligram per liter. Ultimate BOD is 6. River's ultimate BOD is 6. Okay. Discharges 2.73 meter cube per second. River having ultimate BOD and discharge. Okay. Q is 2.73 meter cube per second. That is million liter per day. So 15 into 10 is 10 power 6 is million per day. 24 into 3600 it will give you the liter per second. Again liter to meter cube another 1000 if you divide. So you will get meter cube per second. So this will be equated with this. So what they are asking, assume the temperature of all stream to the remain constant at 20. So this is 20, river is 20, so coming out is also 20. So K is given as 0.26 per day. Velocity is 0.58 meter per second. Answer the following questions. So ultimate BOD they are asking. How to find the ultimate BOD of the river water? Just downstream the wastewater discharge. So after mixing, what will be the BOD? What will be the BOD at the outlet? It's having 15 mld 240. It's having 2.73 meter per second, 6 milligram. So if you just convert the Q value and make it as meter cube per second and just take the average Q wastewater, C wastewater plus Q river, C river divided by total Q, QW plus QR. But all the Q values should be in the same unit. Converted, see, it's converted into 0.1736. Then 240, 2.736 divided by total flow will be 20 milligram per liter will be my ultimate BOD because they are given all as ultimate BOD. Here there is ultimate BOD, here there is ultimate BOD, then the mixed ultimate BOD we have identified. Then second question is same question. 5-day BOD of the river water 20 degree. So how to find 5-day BOD exerted equal to at 20 degree. So how to BOD 5 comma 20 equal to L naught ultimate BOD into 1 minus e power minus k into t. T is time. 5 day. So t is 5. Here 5 na, so it's also 5. 20 degree k. K as 20 degree is given 0.26. L naught we have identified last. 20 is the L naught of the mix. So they are asking just a downstream. So mix. So what L naught we know, K we know, T we know. So we can find BOD 5 at 20 degrees Celsius. Right? So substitute 20 here, K is here, 5 is the T, we can find the BOD 5. Same question, 5-day BOD of the river water sampled from 100 km downstream. So how much time it will take to move to 100 km? Velocity of the river is 0.58 meter per second. How much time it will take to reach 100 km? So if you want time at the top, 100 divided by 0.58. 0.58 is meter per second. So 100 kilometer is 1000 meters. So if you take everything division and then you will get in terms of seconds, right? Then that time, if you substitute in the formula, time this much second, convert to hour, convert to days, 2 days. So 2 days, what is the BOD formula? L naught we know, e power minus k is same, t is 2 days. You will get the BOD at 100 kilometers. 100 kilometer is 2 days. So velocity is known. So if I know the velocity of the river Ganga, and after 100 kilometers, I know how much time it will take to reach 100 kilometer. At that time, if I am discharging this much from my industry, after 100 kilometer, I can find how much it will be there. You got it? Yeah. So that's all about today. I have some more questions. I can try to make a video of that and upload in the YouTube, or I will give you in the this whole notes anyway will be provided with the Google Drive. So all the formula also I will consolidate and give you as a single file. Hope you enjoyed the session, and if you have any doubt, please let me know. I will answer the questions. Thank you so much for joining. If you have any doubt, please ask, or else you can leave the meet. Thank you all. Thank you so much.
Thank you very much.
Yeah, thank you so much. Thank you. Thanks for joining. Hope you all have registered the examination. It's over already. Thank you all. You can leave the
Yes,
meet.
sir.
Yeah. Okay. If you don't have any questions, let me end the meet. Thank you all for joining. I'll close the meet.